What's up, guys? My name is Rustagi, and today I'm going to be teaching you everything you need to know about Unit 6, Simple Harmonic Motion from AP Physics 1. And if you haven't already, please go to the description right now and get my free AP Physics 1 book. Now, that book has everything you need to know to get a 5 and an A in your class. So now, let's begin. So, let's learn about the basics of oscillatory motion. So basically it occurs when there is a restoring force, and that restoring force causes an object to move back and forth. And then oscillatory motion occurs with a pendulum or a mass spring oscillator, where there's basically a mass attached to a spring, and that mass is moving back and forth. And for a pendulum, it'll be swinging back and forth. Now, there's something known as a period, which is very important when we're working with oscillatory motion. So the period is basically like the time it takes for an object, right, to come back to the point where it left. And basically the period of a spring, it depends on the mass and the spring constant. And the period of a pendulum depends on the length of the pendulum and the gravitational field. So the formulas are 2 pi times the square root of m over k for the spring, and 2 pi times the square root of L over g for the pendulum. Now, amplitude is the maximum displacement from the equilibrium point, and often with the spring, you will conserve energy to find the amplitude. For example, pretend there is an object with kinetic energy, right, and it's moving toward a horizontal spring. Then to find the amplitude, you will simply conserve energy because at the amplitude, there will be no kinetic energy. So basically, all that kinetic energy will become like spring potential energy or even gravitational potential energy for pendulums. Now, let's pretend we have a spring with no block right now, but then a block of mass m moves at a velocity v and it sticks to the spring. Now, what is the spring's amplitude? Now, we know that amplitude is the maximum displacement from the equilibrium point, so that means the spring potential energy, right, will be maximized. So we simply set the kinetic energy to the spring potential energy, and we equate both. So 1/2 mv squared equals 1/2 kx squared. And now we can write an expression for x squared. And then we know that x squared is mv squared over k. And we can square root both sides to get v times the square root of m over k. And that's the amplitude. Now please pay very close attention to the graphs that will be shown for the spring oscillator. By this graph, right, this is an example of like the displacement from the equilibrium point with respect to time. And I really hope you recognize this as a trig function graph. Because now let's learn some key facts. Well, basically the maximum kinetic energy, right, or the velocity, it always occurs at the equilibrium point, while least kinetic energy occurs at points furthest from equilibrium. And then the maximum acceleration occurs at points furthest, right, from equilibrium, such as the amplitude. And the reason is that that's when the force is maximized. For example, for a spring, right, if it's at the amplitude, then it's stretched super far, right? That means the spring force will be great, so the acceleration will also be greater. And also, most potential energy occurs at the points furthest from equilibrium, while least potential energy occurs like at equilibrium. And the reason is that at equilibrium, right, we have more kinetic energy. So of course, there's going to be like little potential energy. And also, there's one very key difference between a horizontal spring and a vertical spring. A horizontal spring, you don't have to account for gravitational potential energy. But for a vertical spring, there is gravitational potential energy. For example, if I compress a block down a vertical spring, not only is the spring potential energy changing, but gravitational potential energy is also changing, and you'll soon see an example of this soon. Now, frequency is just the inverse of period, and the frequency of a spring depends on the spring constant and the mass, while the frequency of a pendulum depends on the gravitational field and the length of the pendulum. So basically you can see the two formulas above for the spring and the pendulum. Now, for those that want to see an example of how a pendulum's motion looks like, look at the screen. That's how a pendulum moves when it's oscillating. It just goes back and forth. And one thing that you need to know is that a pendulum swinging has a very small angle, right? For example, if you have a pendulum right now at the initial point, right, it's not moving, and if you move it 90 degrees from that initial point, right, then it's not going to have oscillatory motion. And the reason is that the pendulum requires the small angle approximation. You have to displace it a very small angle theta, right? And if you displace it a very small angle theta, like very small, then it can have oscillatory motion. And the reason is that sine theta is approximately theta. Now let's look at a free response question from an actual AP exam. So please pause the video and read the problem carefully. So basically for part A, we want to find the speed of the block at the instant it hits the end of the spring. Well, how would we do that? So when it hits the end of the spring, no compression has occurred at that point. So this is a relatively simple problem because it's dropped from rest. So the initial velocity is 0. We know that it displaces by a height of 0.45, which means like it moves down 0.45. And we also know that the acceleration is g because it's in free fall. So we simply use the equation, the final velocity squared equals initial velocity squared plus 2 times acceleration times vertical displacement. So we don't know the final velocity squared. So that equals to 0 squared because the initial velocity is 0 plus 2 times g times 0.45. So we can expand this to get 9g, which is around 10 if we plug in 10 for g. And then we get that the velocity is 3 meters per second. Now part B wants us to find the forces on the spring when the block reaches the equilibrium point, right? What's the force in the spring? So at the equilibrium point, the net force is 0. And this means that the gravitational force is balanced out by the spring force. So spring force equals to mg. And we already know the mass, and then the gravitational field is 9.8. So that means the spring force is 19.6 newtons because you simply multiply both to each other. Now the problem asks us to find the distance that the spring is stretched at the equilibrium point. Again, I'm going to highlight the difference between a horizontal spring and a vertical spring. For a horizontal spring at the equilibrium point, it won't be compressed or the spring won't be extended or anything. And the reason is that there is no force in the x direction other than the spring force. But for a vertical spring, there's gravitational force always that's downwards. So to make the net force 0, which is at the equilibrium point, there must always be a spring force. So we already know. So basically we know that mg equals to kx, and then we can divide both sides by k to get x equals to mg over k. And we already know that mg is 19.6 newtons, and then k is 200. So we plug that in, and we can find that the spring must be compressed by 0.098 meters. So part D asks us to determine the speed of the block at the equilibrium position. So our initial point should be where this 2 kilogram block is dropped from, because there is no kinetic energy and there is no spring potential energy. So we only have to deal with gravitational potential energy. So basically at the top, right, when it comes down, it loses a lot of gravitational potential energy. So what is the vertical height that it goes down by? Let's think about that. So basically, right, it moves down a height of h plus 6, where h is 0.45 and x is the compression distance, which was 0.098. And this will all convert to kinetic energy and spring potential energy. And then we know the spring is compressed by 0.098, so we plug in all our variables. So the mass is 2, and then we know the height is 0.45. Basically, the height it moves down to touch the spring, and then 0.098 is the amount it compresses. So we must sum that up because that's how much the gravitational potential energy changes by. And then for the spring potential energy, we know that the constant is 200 and it displaces by 0.098. So we plug all of this in, and we're only left with V. So we can solve for V, and we can find that V is 3.13 meters per second. Now part E wants us to find the resulting amplitude of this block. Well, whenever we have a vertical spring, it's tricky because we can't just equate the kinetic energy to spring potential energy. So now let's think about this. There is a simple trick to use for this problem. Whenever we have a vertical spring, you can simply ignore the gravitational potential energy. How though? Well, whenever we have a vertical spring, we can ignore gravitational potential energy when we're finding the amplitude. And to do this, we can convert this to a horizontal spring by equating the maximum kinetic energy which occurs at the equilibrium point and equating that to 1/2 kx squared or 1/2 ka squared, where a is the amplitude. So if we do this, we can simply ignore gravitational potential energy. So we can now solve for 1/2 mv squared equals 1/2 ka squared, We divide both sides, we cancel out the 1 over 2, and we rearrange to get an expression for A. And we can plug in our known values, like we know that the velocity at the equilibrium point, that's the maximum velocity, is 3.13 times the square root of 2 over 200. And that is 0.313 meters. Now for part F, we want to confirm that the maximum velocity occurs at the equilibrium point. Well, past the equilibrium point, there will always be an acceleration that will oppose the direction of velocity. And that means when it moves above or below the equilibrium point, the velocity will decrease, the block will slow down. And that means the maximum velocity occurs at the equilibrium point. Now, part G just wants us to determine the period of simple harmonic motion, and that's simple. We simply use the formula 2 pi times the square root of m over k, and we plug in our known values. So the mass is 2, spring constant 200, and we can simplify to find that the period is 0.628 seconds. So again, I'm going to remind you of one thing. When do pendulum oscillations happen? Well, it happens when the angle theta is so small, right? When it's displaced by a small angle, so that sine theta is approximately theta, and that is known as the small angle approximation. Now, thank you so much for watching this video, and please don't forget to like, share, and subscribe, since that's going to tell me that you guys are truly enjoying and learning from the books and the videos that I've been making for you guys. And don't forget to join the Discord server to meet other hardworking students that are preparing for various competitions and exams, such as the AP exams. And also, don't forget to follow the Instagram, if you have Instagram, to view educational reels and cool animations. And again, thank you so much for watching this video, and I really hope to see you soon back again on this channel.